In 1928, I sat alone with a pen and paper and wrote an equation. The equation described the electron, its mass, its charge, its behavior at velocities approaching the speed of light. Everything a physicist would want from an equation for the electron. It also described something else, something no human being had ever seen, that no experiment had ever detected, that nobody was looking for. The equation knew it was there. I didn't. Not yet. That gap between what the equation knew and what I understood is what I want to tell you about. Because it's not just a historical anecdote about a physicist and a formula. It's something more important than that. It tells you something about the relationship between mathematics and physical reality that I find, even now, genuinely unsettling in the best possible way. Let me start with the problem. Because the equation was the solution to a problem, and understanding the problem is necessary for understanding why the solution was surprising. By 1928, quantum mechanics had its foundational equation, the Schrödinger equation, written in 1926 by Erwin Schrödinger. It described the behavior of electrons with remarkable accuracy. The energy levels of hydrogen, the specific frequencies of light that hydrogen absorbs and emits, which had been known experimentally for decades, followed precisely from Schrödinger's equation. The structure of many electron atoms, the statistics of electrons in metals, the behavior of electrons in bonds, all of it encoded in this single equation. It worked remarkably well. The problem was fundamental and specific. The Schrödinger equation is not relativistic. It treats time and space differently. It is first order in time derivatives, meaning it involves the wave function and its first time derivative, but second order in space derivatives, meaning it involves the wave function and its second spatial derivative. This asymmetry between time and space is exactly what Einstein's special relativity forbids. Space and time, in special relativity, are dimensions of a unified space-time. An equation that treats them differently cannot be correct for particles moving at speeds where relativistic effects matter. For electrons in atoms, moving at perhaps 1% of the speed of light, the approximation is excellent. But the world has fast electrons. Cosmic rays produce electrons moving at substantial fractions of light speed. High-energy physics requires electrons moving fast. At those speeds, the Schrödinger equation gives wrong predictions. The first attempt at a fix, the Klein-Gordon equation. Written by Oscar Klein and Walter Gordon, it was relativistic. It treated space and time symmetrically. But when you tried to interpret its solutions as describing electrons, it produced negative probabilities. A probability is a number between 0 and 1. It represents how likely something is. A negative probability has no interpretation. The equation was mathematically consistent, but physically incoherent. The requirement I set for myself: write an equation that is quantum mechanical and relativistic simultaneously. Correct probabilities, correct relativistic behavior, and, this was my addition, first order in both space and time derivatives, not second order. I believed, for reasons I can make precise, that a first order equation would avoid the negative probability problem. The additional requirement: the equation should be beautiful, symmetric between space and time, compact, elegant. This was not sentiment. I had learned, from examining the equations that worked in physics, that the ones that correctly captured the deep structure of reality tended to have a specific kind of mathematical elegance. I used beauty as a filter. Ugly equations were probably wrong or incomplete. Writing the equation turned out to require mathematics that was, at the time, considered outside physics. The requirement that the equation be first order in both space and time derivatives, while also being relativistically consistent, forced a specific algebraic constraint on the coefficients multiplying the space and time derivative terms. Those coefficients had to anticommute with each other in a specific way, meaning the order in which you multiply them changes the sign of the product. Ordinary numbers don't do this. A times B always equals B times A for numbers. The coefficients needed to satisfy something different. Matrices can satisfy this, specifically 4x4 matrices satisfying a specific algebraic structure, now called the Clifford algebra or the Dirac algebra, named after this application. The consequence? The wave function being acted on by these 4x4 matrices had to have 4 components. Not 1, like the Schrödinger wave function, 4. A 4-component mathematical object, a Dirac spinor. When I examined what those 4 components represented physically, I found something I had not put there. 2 of the components described electrons with positive energy, spin up and spin down. This was expected. What I hadn't anticipated was that the equation automatically produced spin. Electron spin, the intrinsic angular momentum of the electron, discovered experimentally in 1925, had never been derived from any theory. It had been inserted into quantum mechanics as an additional postulate, an experimental fact that the theory accommodated but didn't explain. My equation derived it. Spin half came out automatically from the algebraic structure of the 4x4 matrices. Nobody put it in, it was already there. The other 2 components described particles with negative energy. Negative energy. Let me be precise about why this is a catastrophe. If an electron can occupy a state with negative energy, energy below zero, and if there's no minimum negative energy, then any ordinary electron in a positive energy state will immediately begin emitting radiation and falling to lower and lower energy states. There's no flaw. The electron falls forever. Every atom in the universe is instantly unstable. Matter cannot exist. The mathematics was producing in 2 of its 4 solutions states that seemed to make the universe impossible. The standard response from the physics community: discard those 2 solutions. They're mathematical artifacts. The equation has extra solutions that don't correspond to physical reality. Use the 2 positive energy solutions and ignore the rest. I couldn't do this. The equation was too precisely constructed, too internally consistent, too mathematically beautiful to be wrong. If it produced 4 solutions, all 4 meant something. The negative energy solutions were not errors. They were predictions I didn't yet understand. My proposal? All negative energy states are already filled. An infinite, invisible sea of electrons in every possible negative energy state, everywhere in the universe, present in the vacuum, undetectable because they're uniform, a constant background that doesn't produce forces or radiation. And the Pauli exclusion principle, no 2 electrons in the same quantum state, prevents any real electron from falling into those states. They're all occupied. The catastrophe is prevented because everything that could go wrong has already happened, invisibly, before the universe we observe came into existence. This was a strange idea. I was aware that it was strange. But it had a consequence I hadn't anticipated when I proposed it. If the sea is complete and uniform, it's invisible. But if the sea has a gap, a state that should be occupied but isn't, the gap is visible. The absence of an electron in a negative energy state behaves like a particle. Think about it carefully. The sea normally has a uniform negative charge distribution everywhere. A hole in the sea, one missing electron, means one less unit of negative charge in one location. That deficit of negative charge looks, to everything around it like a positive charge. The hole carries positive electric charge. What is the mass of the hole? Filling it requires exactly 1 electron's mass of energy. The hole behaves as if it has the same mass as an electron, a particle. Electron mass, positive charge, predicted by the requirement that the negative energy solutions of my equation be taken seriously. My first instinct was to identify this predicted particle with something already known. The proton was the only known positive particle in 1930. It was in every atomic nucleus. If the hole in the Dirac sea was the proton, I hadn't predicted something new, I had explained something existing. That would have been satisfying. The mathematics wouldn't allow it. The hole has to have exactly the same mass as the electron. This isn't approximate, it follows precisely from the structure of the argument. The hole is defined as the absence of an electron. Its apparent mass is the electron's mass. The proton is 1,836 times heavier. Hermann Weyl pointed this out directly and precisely. I had no counter-argument. The mathematics was clear. The hole was a new particle, something that had never been observed, something no experiment had detected. A particle with the electron's mass and positive charge, which I named the anti-electron, later called the positron. I published the prediction in May 1931. No experiment supported it. No accelerator had produced such a particle. Cosmic ray research was not yet sensitive enough to have identified one. I was making a prediction based entirely on mathematical necessity. If the equation was correct, and if the negative energy solutions had physical meaning, this particle had to exist. If no such particle was ever found, the Dirac equation was wrong, and I was wrong. Carl Anderson at the California Institute of Technology was studying cosmic rays in 1932. Cosmic rays are high-energy particles arriving from space. Their composition was being systematically studied. Anderson used a cloud chamber, a sealed container of supersaturated vapor in which charged particles leave visible tracks. A lead plate in the middle of the chamber absorbed energy from passing particles. A magnetic field made charged particles curve, positive particles one way, negative particles the other. In August 1932, Anderson photographed a particle track. The track entered from below the lead plate, passed through it, slowing, as expected from energy loss in matter, and curved in the magnetic field on the other side. The direction of curvature indicated positive charge. The radius of curvature, combined with the measured energy loss in the lead plate, indicated a mass matching the electron, not a proton. A proton of this energy would have a different curvature radius, a different pattern of energy loss. This was unambiguously an electron mass particle with positive charge. Anderson published the result in September 1932. He named it the positron. He later said he had been aware of Dirac's theoretical work. He had not been guided by it. He had found the particle through observation, not by searching for what the theory predicted. The equation had predicted it in 1931. The cloud chamber found it in 1932. 1 year. The confirmation was exact. The particle existed. The equation had been right. The generalization of this discovery is as important as the discovery itself. My equation applies to all fermions, all particles with half-integer spin. Electrons are fermions, but so are quarks, the constituents of protons and neutrons. So are all the leptons, the electron, the muon, the tau, and their associated neutrinos. So are all the quarks that compose all the hadrons. Every fermion in the Standard Model satisfies an equation of the Dirac type. The negative energy solutions and the antiparticle prediction they encode apply to all of them. If the electron has an antiparticle, every fermion does. The antiproton, same mass as the proton, opposite charge, was confirmed experimentally in 1955 at Berkeley. The antineutron, same mass as the neutron, opposite baryon number, was confirmed in 1956. Antihydrogen, a positron orbiting an antiproton, was produced at CERN in 1995. Every particle in the universe has an antimatter counterpart. My prediction? From one equation for one particle extended to all matter. The symmetry was universal. Let me tell you what I find most important about this entire sequence of events, not as history, as physics. I was trying to solve a technical problem. Schrödinger's equation was not relativistic. I needed a relativistic quantum equation for the electron. I had specific requirements: first order in space and time, correct probability interpretation, mathematical beauty. I worked through the algebra for months, alone, until I found the structure that satisfied those requirements. The structure I found described the electron perfectly: mass, charge, spin, all correctly. Spin came out automatically, without being put in. That was the first surprise. Then the equation produced 4 solutions where physics expected 2. The 2 extra solutions described negative energy states that seemed to make the universe impossible. I proposed the Dirac sea to make sense of them. The sea predicted the positron. The positron was found. None of the things the equation told me, spin, negative energy solutions, the positron, were things I was looking for when I wrote it. I was looking for a relativistic quantum equation. I found that. I also found everything else. The equation was smarter than I was. I mean this precisely. The mathematical structure I discovered contained information about physical reality that exceeded my understanding of the structure when I derived it. I knew the equation was right. I didn't know everything it was telling me. What does this mean? One possibility. Mathematics is the language in which physical reality is written. When you correctly identify a mathematical structure that captures the deep symmetries of nature, as my equation captured the symmetry between quantum mechanics and special relativity, you discover a piece of reality's own description of itself. The equation knows what's true, not because you put it in, but because the equation is true. It's a fragment of the universe's own mathematics. Another possibility. The extraordinary precision of the relationship between abstract mathematics and physical reality, documented repeatedly in physics, not just in my work, remains, as Wigner said, unreasonably effective. We use mathematics because it works. Why it works, why abstract structures developed by humans capture physical reality so precisely, is a question that doesn't have a clean answer. My own view, I trusted the equation because it was beautiful. The mathematical elegance of the structure, the way the 4x4 matrices fit together, the way spin emerged automatically, the compactness of the expression, was a signal, not a guarantee, a signal. Beautiful equations in physics, in my experience, tended to be right. The Dirac equation was beautiful. I trusted it enough to publish a prediction no experiment yet supported. The experiment confirmed it 1 year later. Trust the mathematics. When the equation tells you something you didn't ask it, something unexpected, something that seems impossible, something nobody has yet seen, consider the possibility that the equation knows something you don't. It has happened before. It happened to me. In 1928, alone with a pen and paper, the equation said, "There is a mirror. Every electron has a partner." I didn't fully understand what it was saying, but I was careful not to discard it.